for tuning in. We are going to be recording, so thank you, Sarah, for hosting that. Um, and let's get right into it. I'm Corinne Greenberg. I'm the subcommittee chair of our Louisville-Jefferson County Local Emergency Planning Committee. Our particular subcommittee has taken on the challenge of developing this public-facing course with regard to chemical hazards, and let's jump right into it. Okay, so I'm going to start off just with some images here to get us all kind of thinking in the same direction. As these things come up on the screen, what do they all have in common? Of course, all of these things are made out of chemicals. They're synthesized, they're manufactured. None of these things appear naturally in nature. They're all synthetic chemicals. Okay, so about this course. So I do work in industry. I'm actually the environmental health and safety manager at one of the chemical companies in Rubbertown. And in industry, whenever we have new hires joining our team, their first day of new hire orientation, they get this chemical hazard communication course. Now, in the workplace, of course, OSHA requires us to have this course. And so I've been doing this course for new hires for decades, right? And some of these new hires to our company may be coming from another company where they have some experience. Some of them are 20-something-year-old young people starting their first professional job, and they're starting from scratch. And so we got used to having this conversation, presuming no previous knowledge of chemical hazards and chemical safety. And when the question came up, we thought, well, we can turn this around and do it for our local community members as well. So the language that we're going to be using goes back to our training required by OSHA, the Occupational Safety and Health Administration. And of course, they do require this training in the workplace. It's called hazard communication training per their hazard communication standard. And it's all based on the premise that employees have the right to know about the hazards of chemicals in the workplace. So this is fundamental. It goes back to OSHA's 1980 HAZCOM standard, and we've done that. Like I said, we're doing this training in the workplace, and we thought, well, we can share this exact same information with our neighbors in the community. So who else has the right to know? EPA also has a set of regulations called EPCRA. That's coming out of the Emergency Planning Community Right to Know Act of 1986. And EPCRA has several different regulatory programs underneath it, but it's all founded on the principle that community members also have the right to know about hazardous substances in our communities. So that's kind of what this EPCRA rules are, the foundational program behind the Local Emergency Planning Committee. So it's this EPCRA 1986 Act that established local emergency planning committees in every county across the United States. And it also established our state emergency response commission. So this is kind of our mission and what we're here to do. Okay, so we do get our authorization from EPCRA, and we're here to have this conversation. And we think that along with the right to know comes the responsibility to understand. And we actually think that knowledge is power, and this should not be a secret. We know there's a lot of interest, a lot of concern, some good communication, some not so clear communication. And we're here to try to give everybody the same language and the same foundational tools so that we can have this conversation starting from the same place. Okay, so let's start off at the outset with the definition of hazardous chemical. Now, this is the definition from OSHA's hazard communication standard. So a hazardous chemical is any chemical which may be classified as a physical hazard or a health hazard or a simple asphyxiant or a combustible dust or any other hazard not otherwise classified. So this is OSHA's definition. If you think of it, this is like the circus tent. This is the biggest, broadest definition. Almost everything that any other agency or regulation is going to touch is going to fall under this big, broad circus tent definition. Now, within this big, broad circus tent definition, you have the Department of Transportation that regulates hazardous materials and transport. That's going to be like one ring of the three-ring circus. And then you have EPA that's going to regulate the release of hazardous substances into the environment. That's like another ring within the circus. But this big, broad circus tent definition is basically anything that can hurt anybody in any way. Now, having said that, just because a chemical is hazardous doesn't mean it has to be dangerous. I want to say that again for emphasis and clarity. Just because a chemical is hazardous doesn't mean it has to be dangerous. Okay, I've been saying this exact clause in the training room with employees for well over 25 years now. So what's the difference? Okay, so that if we know that a chemical is hazardous, and we know the hazards of that chemical, and we know how to manage the hazards of that chemical, and here's the important one, and we do effectively do the thing that allows us to manage those hazards, then we can mitigate the danger. Okay, the hazard is inherent to the chemical, but when we layer it with management, knowledge and management, we can mitigate the danger and make it not so dangerous in the workplace or in transit or wherever this chemical is used. Okay, so whenever we talk about hazardous chemicals, we can slice and dice them several different ways. We can look at the hazard type of a chemical. Does it have a physical hazard or a health hazard? And we will discuss both of those. We'll talk about the four broad overarching categories of chemical hazards being flammables, corrosive, reactives, and toxins, and we will talk about each of those in turn. And then we can talk about whether these chemical hazards have acute effects or chronic effects, and we'll explain what we mean by that too. So starting off, physical hazards versus health hazards. So a physical hazard is something that the chemical is going to do, period. End of story. Whether or not there's a person anywhere around to be injured, it's kind of like a tree falling in the forest. Does it make a sound? Of course it makes a sound, even if there's nobody around to hear it. So when we talk about chemical hazards, I got a couple examples for you. Acetylene is a highly flammable gas. Acetylene will burn when it reaches an ignition source. That's what it is going to do. Even if there's nobody around to be burned by it, the flammability of the chemical is its physical hazard. It's what the chemical does. Another example, sulfuric acid is a very strong corrosive acid. It will corrode metal. So if you put it in a metal drum or a metal vessel or a metal tank, it will corrode that steel. That's what it does. The chemical does these things. So those are physical hazards. So if you look this image on the right, we have this big, broad outer circle. The outer ring is all the chemicals everywhere. Everything that you can see, touch, breathe, it's all a chemical, right? Within the whole universe of chemicals, there's a subset of hazardous chemicals. So if a chemical has any hazard whatsoever, it's in that inner ring. Within that, there's this other ring called health hazards. Now, a health hazard is the hazard of a chemical, something that it will do to you, something that it will do to me. So this is where you have to have somebody who can get injured. So that same sulfuric acid that's going to corrode through steel, if you get it on your skin, it will cause a tissue burn. So that's the health hazard of sulfuric acid. Another example is asbestos. Asbestos are teeny tiny itty bitty little fibers that when inhaled, they can embed themselves in your lungs and cause scarring, which we know as asbestosis, or they can even be a contributing factor of certain kinds of lung cancer. Okay, so when you inhale asbestos fibers, that is the health hazard of asbestos. Coincidentally, all of the physical properties of asbestos are absolutely fantastic. Asbestos is a great insulator. It's flame resistant, fire retardant, not electrically conducive, not chemically reactive. It's absolutely wonderful stuff. Humankind has been using asbestos for over 2,000 years. The Greeks knew about it and used it. The ancient Romans knew about it and used it. It's a naturally occurring mineral from the earth. Its physical properties are wonderful. But in the mid to late 1980s, the toxicology caught up with us, and we realized that in spite of all its fantastic physical properties, it has some really serious toxicity issues. And so it has these serious health hazards. So that's why asbestos is a hazardous chemical. Benzene is a constituent of gasoline, and benzene specifically is a carcinogen, meaning it's a cancer-causing substance. It's either known or reasonably suspected of causing cancer. It's notable that not every chemical has been linked to cancer. They're actually a very limited subset of the larger group of toxins. A toxin is something that will affect you by poisoning you in some way. Those are a subset of health hazards, which would include things like corrosives that give you a tissue burn. And those are, of course, a subset of hazardous chemicals, which are a subset of the universe of chemicals in general. So the image on the right there, they're like Russian nesting dolls. And we will see this image again. I believe it comes in later in this slide deck. I know we'll revisit it next week as well. Another way of looking at chemical hazards is by the type of hazard, how the hazard manifests itself. And so broadly and generally, all hazardous chemicals fall into one or more of these four hazard types. They're either flammable and or corrosive and or reactive and or toxic. And on this particular slide, you see I put up several different pictograms. We'll talk about those later. The only reason they're on this slide is to suggest that even within one of these broad categories, there are going to be subcategories, subsets. So this is like the 90,000 foot view, flammable or corrosive or reactive or toxic. So let's look at those. The first broad category is things that we're going to call flammables. Now, these are defined, classified, categorized by different regulatory agencies by their different criteria. So OSHA is going to classify any liquid with a flash point less than 200 degrees Fahrenheit as flammable. So what do we mean by flash point? The flash point is the lowest temperature at which a flammable liquid will give off enough vapors to ignite. So your material has to be heated to this temperature in order to ignite. We're concerned about the ones with flash points less than 200 because that's close to the temperature range at which we live, breathe, and work. Okay. I mean, obviously, we're not working in a 200-degree environment, but you can, let's say, in the event of a building fire, you can get to a 200-degree atmosphere pretty quickly. So that's OSHA's cutoff. Now, DOT, the Department of Transportation, they have other interests, right? So they're going to break it into two categories. They have true flammables, which they regulate with a flash point less than 140. So it's much closer to where we live, breathe, and work. But they have this other category that they call combustibles that they are going to regulate. Those just have to be heated a little higher to a flash point between 140 and 200. And then EPA, the Environmental Protection Agency, particularly when they're looking at categorizing things as whether or not they are hazardous wastes, those are going to be liquids with a flash point less than 140. Okay. Now, also in this big, broad category of chemical hazards, this big, broad, flammable category, we're also going to consider oxidizers. An oxidizer is a chemical compound that gives off oxygen. It has excess or loosely attached oxygen molecules that tend to come off in. The hazard there is that they feed oxygen to a fire. So flammables and oxidizers are not the same, but what they both have in common is that they will make a fire situation much worse. One of it gives you fuel to burn, the other one gives you oxygen to feed the fire. So we're going to put all those in this big broad category here. The next broad category is corrosives. So I'm going to take you back to high school chemistry class, and we have this pH scale on a scale of 0 to 14. And right there, absolutely dead center in the middle, at a pH of 7.0, you have pure water. Absolutely chemically pure water would have a pH of 7.0. Now, on the scale at the bottom, you'll see the color shading is deliberate and intentional. So between 6.0 and 9.0, I've shaded that as blue, calling that a neutral pH. And that's the range that is allowed by EPA's Clean Water Act. So as an example, my facility has a water permit for discharge of water leaving our facility, and the water leaving our facility is permitted to go straight to the receiving body as long as its pH is between 6.0 and 9.0. And of course, we have other criteria for other parameters, but specific to pH, 6.0 to 9.0 is considered neutral enough for a natural aquatic environment. Anywhere south of 7.0, anything with a pH less than 7 is going to be acidic. Anything with a pH greater than 7 on this 14-point scale is going to be either basic or alkaline, okay? So anywhere south of 7 is an acid, anywhere north of 7 is a base or an alkali. And you got some examples there. Some common acids include milk, orange juice, vinegar, Coca-Cola. Those are all acids. And we got some examples on the high end as well. Seawater has a pH of 8.1. Soap is around 9 or 10. Antacids, when you have an upset stomach because your stomach acids are agitated, you take an antacid, which is a alkaline material, to help neutralize your stomach and get it back to a happier, more neutral range. Now, it's at the far ends of the scale. Anything with a pH less than 2 or a pH greater than 12.5, those are the hazardous chemicals that are considered to be corrosive acids and corrosive bases. The corrosive acids, like the sulfuric acid we used in the other example, they will give tissue burns if you get it on your skin, and they will also corrode through steel. The corrosive bases and alkali, we have another term for this. We call them also caustics. These are going to have an extremely high pH from 12.5 to 14. Now, the interesting thing about caustics, they don't corrode steel. In fact, steel is the preferred container material for like drums and vessels and tanks. But just because they won't corrode through steel, don't take them for granted and think they won't corrode through you. A caustic burn can actually be more serious and as painful as an acid burn. So at either extreme end of the scale, we've got the corrosive hazardous acids and the corrosive hazardous bases, also called caustics. This is the second major category. The third major category of chemical hazards is reactives. Okay, so these are things that are going to react with something else, either to create a hazardous condition and or to generate a hazardous product. And the easiest way to discuss this is with some examples. So I've given you 3 examples here. And again, going back to high school chemistry, you'll recognize some of this. So the first line there shows a reaction of calcium carbide, the CaC2, reacts with water, that's the H2O. Now, this particular reaction is exothermic, meaning it's going to liberate heat. It's going to generate heat as part of the reaction. And the resulting products, when you rearrange all the atoms of the inputs, they get rearranged by the reaction and they come out as acetylene gas, that's the C2H2, and calcium hydroxide, the CaOH2. Now, going in, that blue CaC2 is a dangerous and wet material, and water is just water. Coming out, you have a flammable gas, a highly flammable gas, and that purple calcium hydroxide is a high pH material. So that's a reaction that creates a hazardous product, specifically the acetylene gas. The next line down, you have aluminum powder reacts with water to yield aluminum oxide. Now, that's the material that is an active ingredient in your antiperspirants and deodorants. So that's not really hazardous, but it is the extra leftover hydrogen there comes off as hydrogen gas. So there's your hazardous product that makes this a hazardous reaction. The row on the bottom, you can take that same hydrogen gas, which starts off as a flammable gas. If that reacts with chlorine gas, which is a toxic inhalation hazard, those two react explosively. So that's your hazardous condition. And it also forms hydrogen chloride, which is a low pH acidic material. Okay, so that's kind of how reactions work. Also in this big broad category, we're going to include self-reactives and explosives, anything that can be detonated. Remember, this is not a regulatory definition. This is a big, broad, let's talk about this at the 90,000 foot level. Reactives is our third category. The fourth of the four categories, and the one that is probably the least understood in general, is this category of toxins, okay? So in general, the word toxin means poison, and the word toxic means poisonous. This is one of the reasons why we wanted to have this conversation, why we wanted to develop this course. The media in particular, and social media is even much more offensive in this manner. They'll say things like toxic materials, toxic chemicals, which may or may not be toxic. Toxic is not a substitute for the word hazardous. A toxin is one kind of hazard. Not every hazardous chemical is considered to be toxic, but there are a good number that are. So let's talk about what that means. So this is at that tightest level of our nesting dolls there, right? So we've got carcinogens are considered to be toxic. They will poison you and give you cancer, or any other chemical that can have a toxic effect, a poisonous effect to your system. So I've got some examples there. These are some chemicals you may or may not have heard in the news. 1,3-butadiene, benzene, trichloroethene, asbestos, lead, mercury, carbon monoxide. All of these things are toxic. They have a poisonous effect on your living system. The severity of the toxin can range from being acutely lethal, that skull and crossbones means it's going to kill you quick, and I'll show you these pictograms again later, to the one in the middle, that exploding chest guy there. That's a health hazard that will stop short of killing you quick. It can either make you really sick, or maybe it kills you slow, like a carcinogen. Or a toxin can be an irritant. That would be indicated by that exclamation point. That's something that will have an effect for the duration of your exposure, but if you remove the chemical or you remove yourself, irritants generally, you go back to having no long-term lasting effects. So the range of effect from a toxin varies greatly, but broadly and generally, as a broad chemical category, toxins are things that have a poisonous effect. Okay. Oh, and this is also going to include marine pollutants that have a toxic effect specifically to aquatic environments. Okay, the last way to look at the hazards of a chemical is whether its effect is acute or chronic. So an acute effect is going to immediate, happening here and now. So we're talking about seconds, minutes, hours, maybe days, okay? So if gasoline reaches an ignition source, boom, it's going to ignite right away. If you get sulfuric acid on your skin, you are going to know right away. Those are acute effects. If you eat enough rat poison, enough arsenic that causes you to throw up, that vomiting is an acute effect. Conversely, if you're fed very, very low doses of rat poisoning, you may not feel sick, but you could still die later. That would be a chronic effect. A chlorine gas cloud, obviously, that's one that would have a very acute effect. Carbon monoxide poisoning. So this is it either happens accidentally or intentionally. If you leave your car running inside your closed garage the carbon monoxide will build up and it will kill you within minutes or hours, depending on how big the garage is. And then I put up Roundup on here. So if you got spring coming up and everything's coming back to bloom, and if you use Roundup on your weeds, if you spray Roundup on the first weed and then you circle all the way around your property, by the time you circle back to that first weed an hour later, the leaves on that weed are already starting to turn brown and shrivel up. That is an acute toxic effect. Conversely, a chronic effect is something that is realized over time. So we talked about asbestos before, right? So individuals who are overexposed to asbestos, you are not going to have an acute effect. It's going to be a very long chronic effect. The latency period for asbestos-related disease to manifest itself is upwards of 20, 30, 40 years. This is why you don't see 30-year-old workers with asbestos-related illness. It's diagnosed in 60 and 70-year-old persons who were exposed when they were 20 and 30 and 40. Liver disease can be caused by trichloroethylene. Again, you're not going to develop liver disease immediately upon exposure. It's going to take time to manifest itself in your system. Brain damage caused by elevated blood lead levels. That's a chronic effect. It doesn't come from, I ate some paint chips and now I have brain damage. But children particularly who are overexposed to lead-based paint, this will manifest itself over time. Cancer, of course, is a chronic effect. Almost all cancers are slow growing. And I've added a couple of environmental ones here, for example. So where ozone depleting substances are emitted to the atmosphere, they can eat away and cause holes in the stratospheric ozone layer. Again, that accumulation happens over time and the manifestation occurs over time. We'll talk about this one next week. And then also atmospheric accumulation of carbon dioxide and other greenhouse gases. That is a chronic effect, and we'll talk about that next week as well. Okay, so now that we got a real quick basic vocabulary session on what these chemical hazards are, we want to appreciate that chemicals can have one or more hazards. Some chemicals just have one. Talked about acetylene. Acetylene is flammable. It's highly flammable. It's incredibly flammable. But what it is not corrosive, it is not reactive, and it is not toxic. It is just very flammable. Asbestos is toxic. But as we already said, it's not flammable, it's not corrosive, it's not reactive. In fact, that's what made it so wonderful to use, because it didn't do any of those things. It wasn't until the late 20th century that the science of toxicology caught up with us and said, oh, wait, maybe this stuff is not as great as we thought it was. Now, other chemicals are going to have multiple hazards. And I like the gasoline example here. Gasoline is flammable and toxic. Intuitively, I am absolutely certain that every single person on this call knows this. You know gasoline is flammable, right? This is why when you pull up to pump gas, you're not going to smoke, you're not going to light a match. Everybody knows that. This is also why if you get some gasoline on your hands, you're going to wash your hands. And you're certainly going to wash your hands before you do things like pick up the baby, okay? Everybody intuitively, we know this. So gasoline is flammable and toxic. Sulfuric acid, we know that it's corrosive. What's lesser known is that it is also very reactive and it is also toxic in low dose chronic exposures, okay? So I want to circle back and talk a bit more about toxicity, because this is the one that I think requires more explanation and more understanding. So what makes a toxic chemical hazardous? So in order for a toxin to be hazardous, you need four things to be adversely affected. We're going to call them the source, the pathway, the exposure, and the dose. And if you interrupt the sequence anywhere along this line, if you remove one piece, then the whole exposure chain kind of falls apart. So let's give some examples here. So if we have a factory that has emissions. They go into the air. That's your pathway. The exposure is breathing that in. If the concentration of that chemical in the atmosphere is above its toxic dose, then a person can be sickened. Another example, if you have a spill that gets into the water and people are in the water and the concentration of that material in the water is above its toxic dose, they can become sick. Third example, if we have a discharge to the water and there's fish and we go fishing and we eat the fish, now fish are notorious for bioaccumulation. Whatever the fish eats builds up in its tissue, and then when you eat that fish tissue, you've eaten many, many fish meals worth of the original toxin. If you are exposed at a concentration above the toxic dose, you can be sick. Okay? Now, conversely, if you have the factory and it has emissions in the air, but there's nobody around to breathe it, then you don't have a toxic effect. Or if you can control the emissions to get it down to a concentration below a level that causes illness, nobody's going to get sick. If you have the chemical getting into the water, we can restrict access to the water, or maybe it's just not present in a toxic dose. A couple months ago, I taught this class to some employees at a sister plant of mine up by Cleveland. And I said, who here in the room thinks that Lake Erie is without contaminants? It's completely pure and pristine water. And they all kind of laughed because everybody knew that Lake Erie was not pure, pristine, non-contaminated water. I said, does that mean you won't go to the beach and play in the water at Lake Erie? Because everybody knew that there were contaminants in the water, but they were so dilute that they did not reach that toxic concentration. And then with the fish example, there are some areas where it's safe to eat the fish in a water body. There are other areas where it's not safe. And so we can limit the toxicity, or at least the toxic exposure here. Okay, so there are altogether 4 possible routes of toxic exposure. So this is where we're going to play defense. This is where we're going to put our attention to protect people and other receptors. So there's the inhalation pathway, that would be breathing it in. There's the ingestion pathway, absorption, which is passing through intact skin, or injection. Now, we're not talking about people going around and shooting up chemicals. We're talking, in this case, like an occupational exposure. If you're in the workplace and you cut yourself with a contaminated tool, you can introduce that contamination directly into your bloodstream. Having said that, absorption and injection both require direct physical contact with the contaminant. These are almost exclusively occupational exposures, or you could kind of do them to yourself as a household chemical exposure, right? When we're talking about public health, though, the 2 pathways of concern are inhalation. Everybody wants to make sure that everybody's ambient air is safe and breathable. And we also want to talk about the ingestion pathway. Again, we're not talking about people going around and eating chemicals, but we want to make sure that our drinking water sources are not contaminated. We want to make sure that our food sources are not contaminated. So we want to be very diligent in protecting inhalation and ingestion pathways, because that protects all of us. Okay, so I've used this term dose. Okay, what do we mean by dose? And I am absolutely not going to insult you with my 1 semester of college German, but I will tell you about Paracelsus. He is this 16th century Swiss physician. Paracelsus is the dude. Paracelsus is the father of modern toxicology. Now, what he was a doctor, medical doctor in Switzerland, 1493 to 1541. And he was the first person to make the connection between certain chemical exposures manifesting as injuries and illness. Okay. Up to this point, before Paracelsus, people thought you got sick because you had bad blood or bad humors, or the gods were unhappy with you. And Paracelsus made this correlation between exposure and manifestation. And so he says, all things are poison, and nothing is without poison. The dosage alone makes it so that a thing is not a poison. The short version is, the dose makes the poison. Okay, the dose makes the poison. What do we mean by that? So I'll ask you, what is the difference between a medicine and a poison? The dose. Okay, so if you have a headache and you go to the medicine cabinet and you take 2 Tylenol, you are trying to treat the headache and you are hoping that that dose is appropriate for your signs, your symptoms, and your size. If you go to the medicine cabinet and you chug a whole bottle of Tylenol, you may not have the headache afterward, but you may have a whole other host of problems because you've now overdosed on that chemical. Okay, so dose is important. There's a line between this much is okay and this much is too much. So I've got this really great graphic here. It is British. Okay, well, show you it. That's why it's in metric units. But let's start at the bottom. 13 shots of alcohol. 13 shots of alcohol is enough to cause a lethal effect. That is an overdose level. Unfortunately, every few years, there's a story that comes up in the news. Usually it's young people at college. Usually it's particularly young men at college. And this is cyclical because today's young men were just children a few years ago and they weren't paying attention when it happened the last time. The problem with this dosage, this lethal dosage of alcohol, is that 13 shots is very doable. It is entirely plausible for a highly motivated young person to knock back 13 shots in a limited time frame and then overdose and die because of this overexposure. Okay? That's alcohol poisoning. Now, there is a parallel with the caffeine in coffee. If you drank 118 coffees in one sitting without passing the caffeine from the very first coffee, you can kill yourself based on the dosage of caffeine. The difference here is that I haven't met anybody yet who can drink 118 coffees in the amount of time that it would take to overdose on the caffeine. Then we got this third example, water. So again, this is British. So 6 liters, this is about 2 gallons, right? This is actually a very doable dose, say over the course of an 8-hour day. You know, we're coming up on spring and summer, and here, especially in the workplace, we're going to remind people to hydrate, hydrate, hydrate. You know, 2 gallons is actually a good amount of water for a full workday. Presuming that you are also going to the bathroom and sweating it out and metabolizing it and otherwise processing it through your body. You don't want to have 6 liters all at once. Back in 2007, this very irresponsible, ill-informed radio station, 107.9 KDND FM in Sacramento, they had this radio contest, Hold Your Wee for a Wee. And the contest was, if you're caller number 9, you get to come down to the studio and compete against other audience members. And the person who can drink the most water without having to go to the bathroom or peeing themselves is going to win a Wii gaming system. And so Miss Jennifer Strange, this 28-year-old woman, mother of 3, lucky caller, she got to go down to the radio studios for the privilege of participating in this contest. She didn't even win, but she was one of the finalists. And after a couple hours, she had about 2 gallons of water in a 3-hour period. Didn't pass it through her body. She's got all this in her. They have radio transcript of her saying on air, I feel kind of funny. And the DJs, being DJs, were laughing and making fun of this, and they were joking. So you can't die from too much water, can you? Well, their lawyers really should have checked this out before they ran this particular contest, because in fact, she did go home and she did collapse and die from water toxicity. Too much H2O in her system basically poisoned her to death. So by that note, all toxic chemicals must be dangerous, right? So I want to introduce this other concept. Just because a chemical is present does not mean it is harmful in the amount present. Okay, so let's say that again. Just because a chemical is present does not mean it is harmful in the amount present. So, in other words, the dose makes the poison. Again, I apologize. It's another British graphic here, but it's really great. It shows that apples, pears, potatoes, and in the US, we would call those zucchini, all have naturally occurring levels of certain toxic constituents. I'm going to use the example of the pear containing formaldehyde. Number one, because pears are my favorite fruit, but also, too, I think people can kind of relate to formaldehyde, right? Formaldehyde is the chemical that you smell when you have new upholstery, new carpeting, new furniture that is off-gassing, okay? That's formaldehyde. So formaldehyde is present in a pear at approximately 6/100ths of a gram per kilogram, or 6,000 grams or 1,000 grams of fruit flesh. Okay, so at that ratio, 6/100ths of a gram per kilogram of fruit. I did the math, and if you work it all out, and we know what the toxicity of formaldehyde is based on body weight and yada da da da, you do all the math, and basically an individual would have to consume 587.9 pears, not in a year. Because if you ask me, I could eat 2 pears a day. I could do that. No, 588 pears in one sitting to achieve a lethal dose of formaldehyde from the pears. Okay? All this to point out, just because the chemical is present does not mean it is harmful in the amount present. There's not enough formaldehyde in an average pear, not enough naturally occurring formaldehyde to make you sick. So both things can be true at once, right? The dose makes the poison, but just because the chemical is present does not mean it is harmful in the amount present. So you have to be mindful what the dose is. Okay, so how do we, kind of switching gears here now, how do we know where these hazardous chemicals are present? So in the workplace, okay, within a facility or within, even within a store or something like that, OSHA requires very certain specific chemical labels. And this is from the 2012 updates to their hazard communication standard. This is when US OSHA aligned itself with their international counterparts to create this globally harmonized system of hazard communication. And so these new label elements were required by 2015. So we've now got 10, 11 years under our belt using these new label requirements. So every chemical container in the workplace is going to be labeled with what it is and a way of reaching the manufacturer who can give you more information, name, address, phone number, all that. And then it's going to have a signal word on the label. It's either going to say danger or warning, or maybe nothing else. Danger is a hazardous chemical that is more dangerous than a chemical marked warning, which is a lesser hazardous chemical. Now, if your chemical container in the workplace doesn't say danger or warning, it's most likely because that chemical doesn't meet any of the criteria by which OSHA will consider it to be hazardous. That is, OSHA will consider it not to be a hazardous chemical in the workplace. Okay, so danger or warning or nothing. Now, here's where it gets really interesting. The chemical label in the workplace is going to tell you the hazard statements. This is the hazards of that chemical. So if you have a water reactive chemical, it will say, reacts with water to release a flammable gas. That is a very specific hazard, and that will be stated on the label. You will also have precautionary statements that will tell you how you're supposed to manage that. So if the hazard is reacts with water to create a flammable gas, your precautionary statement will say things like keep container closed, keep away from water, store in a cool, dry place, do not use water for firefighting purposes, all those things you can do to manage and mitigate the hazard. Because remember, just because a chemical is hazardous doesn't mean it has to be dangerous. If you know how to manage it and you do those things, you can mitigate the danger. And then those pictograms I showed you earlier, this is where those come from. It's this new updated GHS version of OSHA's HAZCOM standard. So these 9 pictograms were adopted and put into use, required for use by OSHA and their international counterparts, adopted in 2012 and required by 2015. So for the past 10 years, we've been seeing these pictograms in this form. Some of them are more obvious than others. Personally, I call this slide the good, the okay, and the let's talk about these. So the top row is pretty good. If you see a flaming flame on a chemical container, that does in fact mean that it is considered to be a flammable material. It's going to meet that OSHA definition for a flammable with a flash point less than 200. The Jolly Roger up there in the top center, skull and crossbones. Whenever you see that as an OSHA pictogram on a chemical container label, it means it's fatally toxic, acute toxicity. It can kill you quick. And then the other obvious one is the dead fish and the dead tree. Those are for environmentally hazardous substances or marine pollutants or aquatic hazards. Everybody pretty much recognizes those, and we get those. Okay, that next one, middle row, far left, it's kind of like a Rorschach test. Some people legitimately don't see that for what it is, but it's supposed to be an exploding bomb. Once you see it, now that I've told you what it is, if you see that on a chemical container, that chemical is considered to be explosive. Now, the one in the middle, okay, people think this should be obvious, liquid eating into metal and liquid eating into a hand. Yes, all corrosives do have that pictogram on them, but, and this is where I have to step in as a workplace trainer, not every chemical with that pictogram is corrosive. Because when they were making these pictograms in 2012, they were hell-bent on keeping it to just 9 pictograms. They were not going to go to 10 or 11 or however many it took. They're going to squeeze everything into 9. And somebody said, well, what about chemicals that cause serious eye damage? And they said, oh, that's a good one. But instead of making a separate pictogram, they said, well, most chemicals that cause serious eye damage do so because they're corrosive. So let's have this pictogram do double duty. Okay, so if you see that on a chemical container, it could be corrosive or it can cause serious eye damage. Now, if your takeaway is, okay, well, I just don't want to get this chemical in me or on me and certainly not in my eyes, that's a decent takeaway. Go with that. Middle row, far right, exploding chest guy. He was brand new when OSHA and their international counterparts developed him in 2012. These other pictograms existed in some shape or form somewhere else before 2012. But exploding chest guy was created for the occasion, and he indicates health hazards, not limited to respiratory health hazards, which is what I thought when I first saw it. This could be any chemical that causes a lasting health hazard, including carcinogens of any kind. So as long as it doesn't kill you quick, if it kills you slow or makes you sick, it's going to get exploding chest guy on the label. Okay, the bottom row, we've got this flaming O, which bothers me because it looks way too much like the flaming flame directly above it. Here on this nice clean white screen, it's pretty easy to see a visual difference, or maybe not so easy. But the problem is in a dimly lit warehouse where these labels are at knee level and the pictograms are maybe an inch by an inch, it's pretty easy to confuse the two. As I discussed earlier, flammables burn and oxidizers feed a fire. But if your takeaway here is, oh, whatever that is, I don't want to have it involved in a fire, that's a good takeaway. The one in the middle, bottom row, looks kind of like a rolling pin, fraternity paddle, cricket bat, wine bottle, all sorts of weird things. It's actually the world's worst artistic rendering of a compressed gas cylinder, not only because it's missing the regulator at the top that would make that the interesting part, but also that horribly awful angle of repose. There's not a single compressed gas cylinder that should be angled at that level. All compressed gas cylinders should be either vertically straight up and down. One exception is propane tanks, which may be vertically straight up and down or exactly horizontally perpendicular, but nothing should be at that ridiculously awful angle of repose. And that's not even the worst part of this pictogram. The worst part is that if you know what a compressed gas cylinder looks like, you've ever been to the floral shop and they blow up party balloons, you've seen these things, they're like 8 inches in diameter and 4 or 5 feet tall. This little pictogram is like a 1/2 inch by 1/2 inch, and it's on the neck band of that cylinder. If you need a pictogram of a cylinder to tell you that you're looking at a compressed gas cylinder, I think you ought to have your eyes checked. So not a great pictogram, but they decided that was worth it. And then the last one, the exclamation point, could be a toxic irritant, or it could be ozone depleting substance, or it could be acutely toxic. You don't know because you have to look it up because they stopped at 9. So whenever you see an exclamation point, I tell my employees, this is when you have to look for more information. Read it like a question mark and try to figure out what the other hazard is. Now, some of these pictograms are going to look familiar. They're predated by this DOT system, Department of Transportation labels and placards. You see these on chemical containers. You see them on tractor trailers going down the highway. You see them on rail cars going down the railroad. Some of the pictograms look the same. They'll be familiar here. But what I like about the DOT system, and this particular version dates back to 1994, and prior to that, the 1974 version looked a whole lot like this. What DOT does is they use colors, they use words, so that when you're looking at it, it says flammable liquid, dangerous when wet, corrosive, oxidizer. And they use color, so you can see that red label from a couple 100 feet away. You can see that red placard on the back of a tractor trailer on the highway from a couple 100 feet away. So I do like the use of words and color here. And then there's this other version that predates that. This goes back to 1957, coming out of World War II. A whole lot of chemistry was created specifically for World War II. Here over in Rubbertown, the whole Rubbertown complex was built in 1941, operational in 1942 to make synthetic rubber to support the war effort. Coming out of World War II, these chemistries that had been developed had a lot of commercial value in use and applications. And so in the 1950s and 1960s, you ever watched Dustin Hoffman's film The Graduate? The word is plastics. So all these things were being created and used in quantities that heretofore had not existed. And that posed a hazard for firefighters who were going into these facilities. Let's say prior to World War II, when a fire truck pulled up to a facility that was on fire, it was pretty much a structure fire, and they were going to put it out with water. The roof is on fire, the walls are on fire, the flooring is on fire, the furniture is on fire. Put it out with water. You can't do that with some of these chemical storage tanks. So the National Fire Protection Association developed this tricolor placarding system where blue always represents the health hazard. Think Blue Cross, Blue Shield, blue ambulance lights, blue nurses scrubs, blue hospital signs on a scale of 0 to 4, where 0 is a negligible hazard and 4 is potentially lethal. So you see two chemicals here, one with a 3, meaning it can cause permanent injury. The other one with a 0, meaning, it's got a negligible health hazard. The red field, think red fire trucks, is always for flammability. So again, on a scale of 0 to 4, where 0 means essentially it does not burn, and 4 means it burns very readily. And if it's a liquid, it's got a flash point less than room temperature. Okay, so both of these two chemical examples are very flammable, 3s and 4s. The yellow field is for instability. Think yellow caution signs, blinking yellow lights, yield signs, things like that. This is how stable a chemical is, even in the presence of a fire. The one with a 0 is completely stable, even in the event of a fire. The one with a 3 can be explosive if heated. Okay, so that's how you read these. The white field is most often left blank. Most often left blank. Usually you'll see it like that 043 on the right with nothing in the white field. But if you do see something, it should be one of these 3 approved symbols. SA, meaning a simple asphyxiant. That's something that nitrogen that can displace oxygen in an atmosphere. So that's important to know if you're a firefighter. The strike through W means, for the love of God, do not put water on it. It's water reactive. Don't use water. So that's an important one, especially if you're a firefighter. And then the letters OX, if they appear, that's the firefighter's cue that, hey, this is an oxidizer. It's going to release extra oxygen to a fire. I need to be aware of that and adapt my reaction appropriately. So this system here is usually on fence lines, bulk storage tanks and vessels, things like that. Okay, so that gives us some general information. Where can we get more specific information? And yes, I do realize we've got 4 minutes and we are close to wrapping this up on time. So I want to introduce these 3 additional resources. And after the class, I will email everybody a list of the vocabulary terms and the acronyms that we use, and also some web links for these particular resources. So safety data sheets, NIOSH pocket guides, and the DOT Emergency Response Guidebook. A safety data sheet is a document prepared by a chemical manufacturer intended specifically for a workplace user. Okay, OSHA simply requires that these documents be created and shared, but OSHA is not an SDS police. They are not going out and checking the work. The only person checking the work is the SDS user. So in my workplace, if I receive an SDS that seems incomplete or doesn't seem right to me, I can contact the manufacturer and take up the question with them. Okay, they are going to have these 16 fields in this order. I'm going to show you just a few examples. So section 1, this particular safety data sheet is for a paint material, a PPG brand paint, a white base alkyled. So section 1 tells you what it is, how to reach the manufacturer, stuff like that. Section 2, the top right page, it shows you those pictograms I discussed earlier. There's your signal word, warning. So it is a hazardous chemical. It's just not as dangerous as a danger would be. The hazard statements of this paint. It's a combustible liquid and vapor. It causes serious eye irritation, suspected of causing cancer, and suspected of damaging fertility or the unborn child. And then you have a whole list of precautionary statements, things that you should do to avoid manifesting those hazards. Section 3 is a nice one. It's going to tell you what the constituents, or at least the hazardous constituents of that chemical are. Any hazardous constituent present above 0.1% should be listed there. I'm going to skip ahead to section 9. Now you're looking at 2 different safety data sheets, 2 different section 9s. The one on the left is the continuation of the paint product. It's going to tell you, because this is from the paint manufacturer to the paint user, it's going to tell you your boiling point, your flash point, your density, your viscosity, your volatility, your percent solids, because that is information that paint users want to know. You will see a whole lot of not available, not applicable, that sort of thing, because they don't think that their user needs that. Contrast that with the SDS on the right, which is an example from a caustic, a sodium hydroxide solution. This SDS is section 9 is going to tell us the specific gravity. That's a measure of density. And the flash point is above 200. And it's going to tell you the pH. Now, remember, the paint SDS said pH is not applicable because it's generally understood that paints are not corrosive. But for the caustic, that's kind of a big selling point there. And then it's going to tell you the evaporation rate, but it's going to have not determined for things like solubility and vapor pressure and vapor density and things like that. So it is specific from the user to the manufacturer to the user. Section 11 is called toxicological information. You would think that tells you something about the toxicity of the chemical. You really have to be able to decode it. The SDS is only that table on the left there. The table that I inserted onto the slide or the right, you have to go all the way outside of the SDS to this online resource called the GHS Purple Book, which is the globally harmonized system of classification and labeling of chemicals. You have to take the information from the SDS, look it up in the Purple Book, and then that tells you what kind of a category of hazard it is. So there's a lot of cross-referencing. It's not very highly useful, and certainly not useful in the immediacy of an emergency or anything like that. The NIOSH Pocket Guide is a much better resource. I know we're close on time. If you give me 5 more minutes, I think we'll get there. NIOSH is the National Institute for Occupational Safety and Health. They are the twin sister of OSHA. They were both formed in 1970 as coming out of the Occupational Safety and Health Act, whereas OSHA is a regulatory agency. They're like a police officer. They write the rules and they go out and they enforce the rules. NIOSH is a research organization. So it's like the lab technician, the geeky sister who wears a white lab coat and likes to do experiments in the lab. They teamed up together in 1974 to create this pocket guide that's going to list some permissible exposure limits. These are limits that OSHA intends to enforce based on research that at the time is driven by NIOSH. Every entry in the Pocket Guide to Chemical Hazards is going to tell you all this for all these chemicals. If you look at the chemical and physical properties list there on the right, that looks an awful lot like Section 9 of an SDS, but as a user, I like the Pocket Guide a lot more because it's almost always going to be complete. So here's an example of the Pocket Guide for ethanol. This is the kind of alcohol that we drink. So it's listed as ethyl alcohol, but ethanol is there as one of the synonyms. It's going to show us our recommended and permissible exposure limits. This is the dose, the concentration above which this chemical can start to become hazardous in an atmosphere. It's going to list the immediately dangerous to life and health concentration. This is where it's very hazardous in an atmosphere. It's going to list flash point. That's something that, everybody wants to know how flammable is it. Going to list things like the upper explosive limit and the lower explosive limit, the range at which it is flammable, specific gravity, vapor pressure. We'll talk about that later next week. It's going to talk about some exposure routes. So this one is follows the inhalation pathway, the ingestion pathway, and in this case, CON means contact for the absorption pathway. It tells you what symptoms you can expect above the recommended dose. So not simply exposure to this chemical. Not every exposure is going to manifest in these symptoms. Overexposure will manifest in these symptoms. And then there's the Emergency Response Guidebook. This one is published by the Department of Transportation every 4 years. This is the book that I would recommend in the event of emergency when you need quick information, 2 quick steps to get you information specific to the hazmat incident at hand. You can look it up in the yellow pages by its ID number, like you can see on that placard there, or you can look up alphabetically in the blue pages. And then that's going to take you to the orange guide. Both of those will give you a reference to the guide number. You flip open to that guide 125 page, and it's going to tell you that in this case, toxic and or corrosive gases, this is how you'll respond for a health emergency, a fire emergency, public safety, emergency response, so on and so forth. It literally takes seconds, like 5 to 10 to 15 seconds, and you're looking at this really great emergency response information. This is far more appropriate and effective than looking at something like an SDS that may or may not have the information you need. If the entry is highlighted in green in the DOT Emergency Response Guidebook, we're talking about toxic inhalation hazard. We will talk about these next week. These are the ones that everybody's very concerned about. These toxic inhalation hazards, also known as poison inhalation hazards, these are gases that, if released, can pose a public health hazard. The green guide is going to tell us some initial isolation and protection distances, and it's chemical specific. And it's also, if it's a small spill, do this, but if it's a large release, do that. This DOT is free online and easy to use. I'll send you the link. And it's also great, especially if you have tweenage or teenage kids in the car. You have them look up the placards of the trucks you're passing on the highway. So here we are. Yay, 5 minutes. To summarize, we talked about that OSHA's HAZCOM standard says that employees have the right to know about the hazards of chemicals in the workplace. And then the Emergency Planning Community Right to Know Act, the same act that established our LEPC here at the county level, says that community members also have the right to know about hazardous substances in your communities. We think that along with the right to know comes the responsibility to understand, and knowledge is power. So we created this course. I will send you the vocabulary and the acronym sheets. We did talk about just because a chemical is hazardous doesn't mean it has to be dangerous. We talked about if you know what the hazard is and you know how to manage it and you do the thing to effectively manage that hazard, you can mitigate the danger. When chemicals are considered to be hazardous, they can have either physical hazards and or health hazards. Those hazards can be flammability, corrosivity, reactivity, toxicity, and the effects can be either acute and or chronic. There are 4 pathways of exposure: inhalation, ingestion, absorption, and injection. And those apply to toxins, which are poisons. You need to have a source, a pathway, and exposure, and a dose. Above the toxic dose, the dose makes the poison. Toxicology is the study that where just because a chemical is present does not mean it is harmful in the amount present. We talked about the naturally occurring levels of formaldehyde in fruit. We talked about OSHA's HAZCOM standards been globally harmonized, how they use pictograms, labels, and placards to communicate the hazards of chemicals. Safety data sheets can provide detailed information, but they are limited to what the manufacturer felt they was appropriate to put on there. It's really designed for a workplace user who has time to read through it and can ask questions. The NIOSH Pocket Guide to Chemical Hazard is a much more complete and much more accurate reference for workplace chemicals. And then the Emergency Response Guidebook is designed for quick lookup of emergency response information. Thank you all for sticking with us. 7 minutes over. Hope you'll join us again next week, 12 noon, same bat time, same bat channel. And hope this has been helpful. If you have not already put your name in the chat, that would be helpful to do so. And we will take all your questions in 2 weeks from now. We have plenty of time built into session 3 specific for answering questions. Thank you all so much.